I'd like to introduce you to the Air Arms XTi-50, and far more importantly, I'd like to explain what it is, what it was designed to do, and a little bit of how it does it. But first, I'd like us to understand the brief the design team was given.
Hello, my name is Alan Dennis and I'm the Design and Production Manager here at Air Arms. The XTi-50 came into being because the FTP-900, the predecessor to this rifle, came to its natural end. At this point we decided it was time to have something new, something fresh, and move on to new technologies. The concept of development of this rifle was pretty much the same as previous rifles, except this time we had the focus group, which offered a very fresh and an enlightening view on component parts, use of the rifle, how the rifle should perform, what was expected of a rifle of this standard, things that would make it, give it some longevity in the various disciplines it was going to be used in. The focus group was selected from Air Arms HFT and FT team members, as well as other shooters that have been part of the Air Arms extended family. The entire process was very similar to how we would normally create a rifle, we would come up with an idea, work through prototypes, make models, test them, refine, and then produce. Except this time, obviously, we had a focus group, which was really nice because they were able to give opinions along the way. They were able to help us tune and fine-tune and redesign items that we considered okay, but in the actual real world, perhaps not as good as they could be. This rifle is very different from other air rifles that Air Arms have created in that normally we follow a process of evolution, whereas this time the rifle was basically a bottom-up redesign from everything. We looked at every single component, replaced every component we think wasn't going to do the job needed. Accuracy, consistency, and reliability. These three things make or break a rifle. You can put as many toys and as many gimmicks on the rifle as you like, but if these three things don't work, the rifle's going to fail. At first it was very strange. The process involved several meetings. The first meeting there was about 20 odd people in a room. We had an idea, we kicked it about, they threw opinions in, we went away, and over the next year or 2 years we basically took each of those opinions, tweaked them on the rifle, produced prototypes, sent them back for further opinion, and were able to hone the rifle down to the product we have at the moment. The buttock and cheek piece are critical elements of a rifle. Obviously not the only parts, but these are the parts that particularly fit the rifle to a shooter. They have to be designed in such a way that they can adjust them to make sure that their head, scope, the gun, it ends in the same position every time when they bring it to the shoulder. The journey of producing the XTi-50 has been tough but fulfilling, I would say. We've gone through many connotations, many design changes, but we now have produced a rifle that we can be very pleased with, very proud of, and I think will produce good results for shooters for years to come. One of the very biggest challenges we had creating the XTi-50 was getting the Hamster correct, the forehand adjuster correct. We wanted a level of adjustability and a level of usability that meant it could all be done with one hand, it could all be positioned very, very close to the barrel to reduce the pitch or extended as far as people would want. This piece turned out to be quite a challenge through the time, but I'm happy to say that through all the various prototypes and all the various developments we made, we've ended up with a really nice piece that should do everything everyone wants of it.
One of the unique things about Air Arms is that we manufacture 90% of the components ourselves. The other sort of components that we buy in are fixings, O-rings, springs, etc. The stock made by Manelli, and the barrels of course made by Lothar Walther. Virtually everything else we make in-house. We have at our disposal a number of sliding head lathes, fixed head lathes, vertical machining centres and horizontal machining centres. Here we have a fixture that has the main body, cover plate, cocking arm, various elements to do with the trigger chassis that are all made in-house on one of our horizontal machining centres. The other thing that is unique about us is that we design and manufacture all of our fixtures such as this ourselves. This particular pallet, or tombstone as we like to call them, is on a 20,000 RPM Matsuura. Each time this pallet runs, we produce 2 sets of parts, and there's ultimately 6 components that are produced at every one time. The main body, for example, goes through 4 different stages. Most other components here go through 2 different stages. This fixture itself has 40 bespoke elements to it that are designed so the components such as these that are holding the finished parts. All in all, there's over 400 parts within this fixture, including the fixings and the bespoke components that are made. On the XTi, we've actually got 3 tombstones making components. We have this one here, and on the same machine we have this pallet here. So this is now making a lot of the parts what I would call stock related components. So these are for the cheek piece and the butt pads for the mounting. We have the hamster, we have the housing for the mechanism for the hamster. This component here is the plate that is the cover plate for the hamster. This particular fixture has 8 components running at any one time, and the same again, there's 2 sets coming off every time the fixture runs in the machine. This one has 30 bespoke designs for the fixturing. All in all, there's a little over 600 components on this fixture, including fixings. Finally, on a slightly different machine, but same principle, this is on a 15,000 RPM Matsura. This is predominantly got all the sort of butt pad parts, plus we've got the spacers here for the palm rest. This particular fixture has 15 components coming off at any one time. Every single component goes through at least 2 stages. Some of them are 3 stages, and some of them there are multiple components because of the set. It's effectively 2 sets every time it runs. The fixture is a lot more, although the parts may be more basic and less complex than say the body, but there's a lot more on there. There's 15 components that come off at any one time, and some of them are multiples of. It has in excess of 750 parts in the fixture altogether. It includes the tombstones. These tombstones, as an indication, this is 600 millimeters high. It's 300 millimeters square. Once we then design the fixtures, then it comes to programming. There's an awful lot of detail in what we program. For example, the first one that we saw, which is for the main body, this is an indication of what goes into it. So we work on a principle where we have a main program and then we have sub-programs. Effectively, each individual tool within on that pallet is a separate sub-program. So to start with here, we have the probe. Every time the pallet goes into the machine, we probe it with Renishaw probing, an MP700 probe. At the end of every tool, we use Renishaw NC3 to tool check to make sure the tool hasn't moved, broken, etc. This in particular instance on pallet 7 on our 20,000 RPM horizontal, there are ultimately 100 sub-programs. So that means there's 100, doesn't mean there's 100 tools because some of them are used multiple times. They come in and because of the how we need to machine, and we're bringing the same tools in at different times for different machining techniques. But ultimately, I believe it's in excess of 90 tools to produce that components on that pallet. Okay, so the challenge we have when I'm designing a fixture such as this, first and foremost, it's quite important that we make the most of the space we have available to us. If we look at this scenario here, there's very little blank space where we could fit other components. So that's the number one thing. It's trying to be as efficient as possible with the space we have available. On top of that, you're then into the challenges of how do we grip the component, how do we hold the parts, whether it be the blank to start with. Then as we then move on to different stages, obviously if you look at this one, it's a little bit more complex because the first stage is machining the shape. If we look at this one, this encompasses some of the challenges as well, is you're trying to do as much machining in one go as possible to reduce it down to the minimal number of operations. So in this instance, on the cocking arm, we are machining face on, effectively doing this outside profile here, these little slots, all this detail, these step details, and this hole. And also, we do this 3-axis machining as we then produce these little scallops, and they are produced front on here. Then obviously, as we then look from the side, we are machining this outside profile here. So when it then comes to onto this operation, all this machining has been done. So now we're looking to retain it properly, so we can now effectively machine the outside face, removing the sacrificial material we were holding on the first operation. So that's part of the challenges, is gripping something through all of its stages, getting as much on there as possible, ensuring that we machine as much in one go in possible at each time. So on this scenario, on the main body, we are machining from the front face, we are machining from the end, and we are machining from that end. So effectively, the really critical areas from a line-up perspective and the relationship between the bore and the chassis area is all done in one machining operation. So you are reducing the risk of errors in regard to location as you move to another operation. Obviously, with this as well, you see from the size of this, we have challenges in regard to our tool lengths. You've got to imagine there's a big spindle spinning around here, so we've got our tool lengths. In the ideal world, all of your tools are as short and as compact as possible. These are very advanced tools, whether they be carbide, special coatings, special geometries for machining aluminiums. And the same with the milling cutters as well. We are using our milling cutters that we use are all very high quality, with geometries that are specific for machining aluminiums at higher spindle speeds and higher feed rates, and achieving the finishes we want as well. One of the critical things for us is surface finishing. So when you come to that rigidity, when you come to machining, rigidity is one of the key things to give you good surface finishes, and that's also very important in our grip and our location. These particular parts here, little wedge clamps, they have immense clamping forces, so it does give us good rigidity. And these blocks are reasonable size. You can physically see a bit later on when you see the fixtures on the film. They're rigid, they're doweled, they're screwed. These are M8 or M10 cap heads here. They've got immense forces holding everything in place, and they're 8mm dowels here, so you don't get any deflection and you get maximum rigidity on everything that we do. And that then ultimately ensures that we produce the quality of product that is synonymous with Air Arms and critical for a product of this quality and price point.
When this thing was conceived, it's got a very simple job, it would appear. It has to virtually put pellet on pellet out to all the field target ranges, because that's what it exists to do. It exists to win world championships, where one target dropped could mean the difference between winning and being the runner-up. To do that, it has to perform like a surgical instrument over thousands and thousands of training shots and the all-important shots in competition. But it has to do more than that. Unlike paper target rifles, it doesn't do it within a controlled environment. It has to do it at minus temperatures and up to +40 in the rain, the wind, with the dust, mud, all sorts of things going on around it, and it must never ever miss a beat. In order to get to that level of efficiency, the amount of input required is off the scale. I've been covering this sort of thing for 30 years, and I've learned more about how to produce something like this through the XTi-50 than I've ever known in all those decades before. For instance, just the Hamster here, this wonderful component, this support, that is months and months, bordering on a year of development just to get that thing as it should be. And the reason for that is the Air Arms standard. They bring in world champions, they bring in national champions, they bring in a think tank of the most discerning shooters on the planet. And they ask them what they want. And then they have to give it to them. And remember, this thing, it can't just perform to that brief. It must do it every time to build the absolutely vital component of shooter confidence. Because if anything gets in there that this thing isn't going to deliver shot after shot, then the whole deal has gone. Shooter confidence can't be bought, you can't get it off the shelf. It can only be earned through thousands and thousands of reliable shots under those conditions I mentioned earlier. The processes involved in renewing every single major performance component within this rifle, and they were, every one, there are over 450 components. If any one of them doesn't do its job, the whole system goes. So they must do their jobs under every conceivable condition. There are different types of O-rings inside here, different types of fastenings, different types of metals used, processes used to produce these major components, even with the state-of-the-art computer-controlled machinery. The complexity of it is incredible, and there is only one standard. Always right, always spot on, every time.